Welcome to my JK Solutions channel. This video is about electrical power distribution system, transformer sizing calculation, as well as 33 kV skipper metering panel. So, as I said, in this video, we are going to see another type of distribution system, another type of power schematic diagram, as well as another calculation on transformer sizing. We are also going to see how to do metering at medium voltage, which is 33 kilovolts, without necessarily making use of the conventional AC or MV panel. Meanwhile, please do subscribe to my JK Solutions channel if you have not done so, and then please you can expect more informative and more educative videos on this channel. Thank you. Please, in this video, anywhere mechanical interlock appears, it is meant to be MIE interlock or automatic changeover system. Mechanical interlock alone is a manual changeover switch, while MIE interlock means automatic changeover switch. Thank you. For proper understanding as well as thorough understanding of the concept, it is always better to make use of an example. So please continue to watch the video as I go through the example. Alright, and the example is electrical power requirement of a building is collated as 700 kVA. So the questions are: A part, calculate the building load, delta line current at 33 kV, 50 Hz, and star current at 400 volts line to line at 50 Hz frequency. So B, draw the schematic diagram for the distribution system. C, hence or otherwise determine the transformer size for the building. Neglect transformer losses. Once again, anywhere mechanical interlock appears in this video, it is meant to be MIE interlock or automatic changeover system. MIE interlock means automatic interlock, while mechanical interlock means manual. In this case, we are dealing with automatic, not manual. Now, the solutions to the problems. A, first part of A, delta line current. We can make use of this simple diagram here. Alright, this is the delta and this is the star. Alright, even though we've not reached the stage of transformer, but we have to calculate the delta line current. This is the current, this current I, this current I, okay, is the same for the three lines. Alright, so if we do that, now the line voltage is 33 kV. 33 kV. Alright, so if the line voltage is 33 kV according to the question, now the apparent power is equal to square root of 3 times line voltage times line current. So from there we have I line. Alright, I line is equal to S divided by root 3 times VL. So S, the apparent power according to the question, is 700,000 VA or 700 kVA. So the square root of 3 is 1.7321. Then the line voltage, which is this voltage, the voltage between two lines, is 33 kV according to the question. So this is what we have here. And when we calculate this one, if it is properly calculated, this is the answer: 12.2 ampere triple phase, because we have we have 3 phases here, 1, 2, 3, and 3 lines as well of equal magnitude of current. So that is the solution to the first part of A. Now the second part of question A, the star current at 400 volts line to line at 50 Hz frequency. So just similar to the first part of A. So the line current in this case is this 700,000 VA divided by 1.7321 times 400 volts, and the answer is 1010 ampere triple phase with neutral. We have neutral here. This is the delta. This is the star side. This is delta. This is star. So when we have star, we have neutral points. So it doesn't mean that the neutral current is 1010 ampere also. No. We can, for a balanced load system, the neutral current will be 0 in this situation. But when when we have a load that is not balanced, then one can calculate the neutral current, and that will be a topic for the future. So we are going to do that one in future. Alright, this is the solution to the second part of question A. The schematic diagram for the system. Alright, the star LV line current, which is the same thing as phase current in star. When we have a star connection, the line current is always equal to the phase current, and is equal to 1010 ampere. That is 1010 ampere. Alright, this is the load current. Alright, so because from 700, if you have a 700,000, we divide it by 3 times 400. Alright, and that is the current I line, which is equal to I phase. The answer is 1010. Okay, so if you have 1010 as the total current, so the first thing, first of all, the load, this is the load. Load is equal to 700 kVA. Okay, if we have 700, then we must select generators that will give us power. Yes, the apparent power that will be slightly greater than 700. So we can make use of 500 in combination with 300 kVA. We could have used 800 kVA generator, but it is better to have two, so that as the load changes, as the load fluctuates, one of the transformer, of the generators could be shut down, as the case may be. So if we take the 500 kVA and 300 kVA generator, they will serve the purpose. So for the 500 kVA, we use 630 amp circuit breaker MCCB to protect it. So this is MCCB. Okay, and this is also MCCB. So for the 300 kVA, we use 400 amp circuit breaker to protect it, because the maximum current that can be drawn from this one is about 433. So with 400 we protect it very well. This one we can have a maximum current of about 721, so 630 amp we protect it. Okay, so that if we add the two together, it will give us about around 1030. That is 1030 ampere, which is slightly greater than this. So it's still in order. So now we come here, This is the interlock. So we have the same 1000 ampere circuit breaker here. So this is the one we can easily find in the market for this situation. So and then we have the mains. We've been told that the supply is 33 kV. So we have a drop fuse here on the pole, on the electric pole. So this is a 33 kV skipper metering panel. This is the metering panel that can be used for measuring the kilowatt hour. That is the energy meter. It can be used for metering without necessarily making use of the conventional HT or medium voltage panel. So this one, the dimension is just about 1.2, just like this, 1.2 by 1.2 by 1.2 meter in height as well. So it's a very small panel. The skipper, this skipper, the word skipper is the name of the manufacturer of the metering panel, which is the panel is common in some areas or in some parts of West Africa. All right, so we move on. So after the metering, we have 33. We have 800 kVA transformer. This transformer with the primary side at 33 kV and the secondary side at 400 volts. We step it down. We protect the transformer with 1000 ampere triple phase with neutral MCCB. Okay, that is model case circuit breaker. This IPC swap means ingress protection in case it's installed outside or is installed outdoor. So it has to be waterproof. So it has to be enclosed. This is it can also be called encapsulated MCCB. So and then on this side also we have 1000 ampere circuit breaker. So when there is main failure, so there will be a sensing signal. Okay, so sensing signal from this panel to this panel here, this APLS panel. This A means, or this APLS means automatic mains failure panel, and it's also serving as a phase sequence panel, and it's also serving as load shedding, all right, and synchronizing panel as well. So that is what it's doing. So this is a remote sensing line. Okay. Remote sensing line. So this is remote sensing line, and then depending on the signal received by this panel can signal to these generators whether to switch on or to switch off, any of them as the situation arises. So and then here we have the common bus section, this line. So this is the common bus section. So from here we have outgoing circuit breakers. Okay, this is MCCB as well. So MCCB 3. So they are now going to the loads, load 1, load 2, load 3. So the loads could be distribution bus or some other types of loads. Okay, so the magnitude of the load will be the one in each case, or the load will be the determinant of the size of the circuit breakers. That's why I'm not putting the size of the circuit breakers there. All right, so this is the LV panel, 1000 ampere triple phase with neutral MCCB low voltage panel. So and that is the schematic diagram for the system. The C part, the transformer sizing. We have known that the primary side of the transformer is going to be delta, and the voltage is 33 kV at 50 Hz. So on the star side, which is the secondary side, we know that the voltage is 400 volts at 50 Hz frequency. Now, looking at the combination of these two generators, 500 and 300, we are having 800 kVA here. So the size of the transformer, the kVA rating is definitely 800 kVA, and the medium voltage side is 33 kV. The low voltage side is 400 volts. Both sides are at 50 Hz, and it is a step down transformer. So, and this is the size of the transformer. Hence or otherwise means without necessarily not going through any rigor. Deduce, just a deduction. We are deducing the size of the transformer from what we have done in the A part, on A part and the B part. So this is the size of the transformer: 800 kVA, 33 kV slash 400 volts at 50 Hz, step down transformer. Now, and that ends up the solutions to the problem. Finally, if you are new on this channel, or if this is your first time of being on this channel, please do subscribe to my JK Solutions channel. I expect more educative and informative videos. Thank you. Thanks for watching.